All right, so in our last lecture, we developed matrix form of the backpropagation algorithm. Okay, so today I'll talk about the implementation of it in Python and also C#. And the reason being, even though you guys will be doing your implementation in Python, but some of the examples later on, I already have created them in C# so that you can follow at least what the code is supposed to do. Anyway, so let me summarize the key ideas we had developed last time. And the key idea was, let's say we have some inputs coming in. Okay, we'll multiply by the weight matrix. So let's say here's some weights. Okay, and then as we multiply by the weights, then this will go to the neuron where we are summing, right? And then we pass it through an activation function. And so even though there will be a lot of neurons over here, when we code it, we'll code it as a single array over here, or a single object or a single class with matrices being inputs and outputs. Okay, so very similarly over here, suppose there's another layer involved. Okay, so there will be another set of weights that we will go through. Okay, and so again we'll be summing. There will be a bias involved over here. There will be a bias involved over here. Then we'll go through an activation function, and then finally we'll produce the output. So in matrix form, the output will be a vector. The input will be a vector. Okay. And again, there will be many of these, but we'll represent it by one object, which takes a matrix as an input and a matrix or a vector as an output. So the way we developed the algorithm was, because as we write the code, we'll just follow our development over here. So suppose there are two layers involved. Okay, let's call this one layer 1. And let's call this layer 2. Okay, so then to make our coding a little bit easier in the beginning, we'll generalize it later, but let's pretend for two layers, this is called W1, this is called B1, this is called S1, this is called A1, then this is called W2. Okay, then over here, let's call it S2, and let's call this A2. Okay, as the A2 output is produced, okay, we'll have some kind of a loss function over here. Okay, so this will be our loss, and there will be some expected. So Y, if you recall, our terminology is for the expected output. Okay, A is our terminology for the actual output. Okay. So anyway, and let me call this B2 over here, 1. Okay. So our algorithm, if you recall, goes through a double loop over here. So our algorithm will simply go for I equal to, let's say, 0 to number of epochs. Okay. Then and I'm just writing in pseudocode format. If this was Python, you would say for I equal to I in range 0 comma number epochs, right? So anyway, in pseudocode format, J equal to 0 to number of training data. Okay, so somebody will give us training data. Suppose we have 500 of these training data. So this will go through 500 epochs. Typically will vary between 50 or 100 or some number around that. And we'll talk about what should be the proper number of epochs, how do we decide. Anyway, so as we go through this loop, so in plain English, our code will be pick one training sample or training data. Okay, so based on the J index, we can index the J and pick, right? Then do a forward pass. And before this, we will initialize model parameters. Okay, randomly. Okay, and what are our model parameters in this example?
Weights and biases.
Yeah, so this will be W1, W2, and B1 and B2. Right? Okay, so once we've initialized them randomly, then, like I said, we'll do the forward pass, and I'll give you more detail in a second. Okay, then after we have done the forward pass, here we'll basically store A1, A2. Okay, because as we are passing the data through, whatever is the value of A1, whatever is the value of A2, we'll store it, and of course we'll compute S1 as well before we do the computation of A1, right? Okay, then we now do back propagation. So based on our loss function, so based on loss, okay, we'll do the back propagation, okay? And as we do the back propagation, the idea over here will be to compute the gradients. And in this case, suppose we represent our gradients like an inverted triangle. So del W1, del W2, del B1, and del B2. Okay? As we are computing the gradients, if you recall last time we discussed that what we do is in the middle of the neuron, if you can think of this as a delta, so for example, let me call this delta 2. In the middle of this neuron, let me call this computation delta 1. And delta 1 is basically the accumulation of the derivatives, the chain of derivatives up to that point. So if we started from the partial loss up to this point, so you can see delta 2 basically is partial L over partial A2 time partial A2 over partial S2, right? Okay, so once we have computed this delta 2, then what we do is we go backwards and compute delta 1 from delta 2. So from delta 2, how will we compute delta 1?
So the weights.
Okay, because the weights are the one which is joining these two. So first we go up to this point. Okay, so the derivative up to this point will be basically delta 2 times W2. So delta 2 times W2. Okay, then further, the derivative of partial A1 over partial S1, okay, whatever is that activation function. So that's the computation of delta 1. Okay. Once we have the delta 2 and the delta 1 computed, then these gradients are very easy to compute. So for example, let me see if you guys remember, how will we compute the gradient with respect to W2? Okay, if you recall, the definition of this was that whatever we have the gradient up to this point, I mean the chain of derivatives up to this point, we further have to go, so up to this point is delta 2, correct? Multiplied by partial S2 over whatever the previous output is, partial A1, right? Okay, if you now take a look at the expression for S2, what is the expression for S2 in terms of the matrix equation? W2 multiplied by A1, right? So W2, no, because A1 is acts as the input feeding to this one, right? Plus 1 times B2. So now if you did a partial S2 over partial A1, what will you get?
Wait.
Sorry, did I make a mistake? I want partial A1.
The balance must be W2.
Okay, it should be W2, correct. Because I want well, my goal is to find, so not the
Yes,
delta 1, okay, delta 1 was okay. Okay, let me just see. Delta 2 times W2, okay, plus A1 over S1. Okay, so A1 over S1. Okay, so that's the delta 1. So the gradient will be now, this will be S2 over W2. Because we want the derivative with respect to W2, right? So now go to this equation and take the derivative with respect to W2. So what will this come out? Okay, this was delta 2. Okay, so this will be delta 2. Okay, with respect to W2 will be A1, which as we try to reason or try to intuitively figure out last time, basically the derivative with respect to the weights is whatever the delta here is times the previous input. The previous input over here is A1, right? So very similarly, can you right away tell me what will be the gradient with respect to delta 1?
Delta 1 into X.
Sorry, del of W1. Delta 1 times whatever the previous input is. What is that? X. So that will be X. Okay. Very similarly, what will be gradient with respect to B2? Okay.
Just like that.
It will be simply delta, because over here this will become partial S2 over partial B2, which is 1. So this will be simply delta 2, right? And lastly, what would be B1? It will come out to be delta 1. So these are the computations that we will be doing. Once we have all the gradients computed, then we go and update the weights. So W2 will become W2 minus the learning rate times del W2. W1 will become W1 minus the learning rate times del W1. B1 will be updated as B1 minus this times del B1. And lastly, B2 will get updated as B2 minus del B2. Okay, so anyway, that's our algorithm. Just compute these. How do we compute these? Once again, to compute these, first you will compute the delta 2 and delta 1. Okay. Then from the delta 2, delta 1, we can easily compute the del W2, del W1, del B2, del B1. And once we have that, then we update the original W's based on the learning rate. Okay. So now we'll develop the code, and you will see the code that we write will 100% mimic exactly what we did over here. Okay. And I'll show you both Python as well as C# code. Okay. So now in your next assignment, you'll be dealing with, see, our first assignment was pretty toy example, just do y equal to 0.3x plus 2. So now we'll start to do some classification on some real data. So one of the popular, as you're doing, deep learning, one of the popular data sets is called MNIST data set. So let me give you an idea of what this is. Then we'll talk about how will we implement this for our neural network. Okay, so the MNIST data set is basically images. So there are images of digits. So they look like this. Here's 0, 1, and 0 through 9. Okay, so these are handwritten digits, black and white images. Okay, 0 through 9. So as you can see, there are basically 10 classes involved over here, meaning 10 categories, 0 or 1 or 2 or 9, right? Okay. Now in the MNIST data set, each one of these images is 28 by 28 pixels. Okay. So once we read the image, it will be read as a pixel value, and the pixel value basically is like each dot represents a pixel. In the grayscale, the red, green, blue are all similar, and each dot basically varies from 0 to 255. If it's 255, it's white color dot. If it is 0, it's black color dot, right? And in between, it could be a shade of gray. So anyway, as you can see, let's say we have this image, right, of a 0 or 1 or a 2. So there will be some pixel values over here like 0, 0. First row may be all zeros, but somewhere over here you'll see 240 or 250 or something like this, right? Okay, now when we feed the data to our regular dense network, okay, later on we'll be doing convolutional neural networks where we can feed a two-dimensional data, okay? But for our dense networks, which are basically regular, fully connected networks, meaning every input goes to every neuron, every output over here goes to every neuron in the next layer. So for dense networks, we linearize the two-dimensional data. So if we wanted to feed an image to it, we'll basically linearize it, meaning convert it to a 1D array. Okay, so how do we convert it to 1D array? You basically go row by row, so use whatever those values are. So let's say the first row of these 28 numbers is all zeros, right? And then somewhere over here, the second row or the third row, you'll see 240, 250, and so on. So basically, row by row, this is the first row, second row, third row, all the 28 rows we put in one vector. So if we assemble it into one vector, as you can see, the size of this will be 28, 28, which is 784 times 1. So every digit that we feed to our network will be basically 784 digits. Okay. So now let's talk about it. If we wanted to set up this network, what will be the dimensions of all of our variables over here? Like we discussed, they are all matrices. Okay. So if the x is going to be 784 by 1, okay, let's pretend we wanted to use 100 neurons over here. Okay, so what will be the size of this weight matrix? Okay, so we have two choices, 784 times 100 or 100 by 784. Which one will we choose?
100 by 74.
Okay, this is the correct answer. And the reason is, if you recall, when I was drawing like a simple neural network, okay, let's say x1 and x2 are the inputs. This goes over here, this goes over here, and all of these go over here as well as here. Okay, so let's say we wanted to put a name to this weight, okay, like a variable name. So as we discussed, the way we will write it is output number, comma, input number. So then this will be W31, because this is the third output, 1, 2, 3, and then 1, right? So this, so doing it this way, we were able to, if we have to represent, for example, all the sums over here, we can write it as a matrix equation Wx plus B. So if we didn't do it this way, then this does not come out proper. So because the output number always comes first, as far as the size of this matrix is concerned, it's also dictated by the size of the output first, then the input. So since we said we'll use 100 neurons over here, size of the output is 100, input is 784. So the dimension of W1 will be 784 by 100, correct? Okay, so now if you can tell me what will be the dimension of S1.
Same, right?
100 multiplied by the number of neurons.
How many neurons do we have?
100.
So there will be 100 S's, right?
Yes.
So the size of this will be 100 by 1. Because this is the output of the sum inside a neuron, right? As we are doing the forward pass. Very similarly, can you tell me what will be the size of the A1 matrix? A1 is same as S1, right? Because for example, if our activation is sigmoid, we're applying sigmoid to every input. So if there are 100 inputs, there will be 100 outputs. So this will be 100 by 1. Okay, let's go to the W2 size. Okay, W2, again, we go output size, then the input size. What's the output size? Okay, let's decide how many neurons do we want over here. Okay, because in our example, it's just a two-layer network. Okay, the number of neurons, see this one we can pick ourselves, like 100. Here we don't have a choice because we have 10 categories total. Okay, we have to have 10 neurons in the last layer. So the last layer depends on the number of classes. Okay, I mean there is a way we can pick one neuron and do a range, like 0 to 0.1 means it's 0.1 to 0.2, but that doesn't work as well. Okay, typically if we have 10 classes, we'll use 10 separate neurons. Okay, so this is given by the problem to be 10 neurons. If we are doing, let's say, MNIST digit recognition. Okay, so now my question is, what should be the W2 then?
10 by 100.
Output is 10, input is 100, so 10 by 100. Can you now tell me size of S2, which is the sum inside the neurons?
10 by 1.
10 by 1, perfect. A2?
10 by 1.
Okay, so now that we have all the dimensions over here, let's talk about the forward pass and see from because we'll be doing matrix operations, so we have to make sure that the matrices, when they are being multiplied, added, they work properly. Okay, so for example, let me go to the forward pass over here. So let's elaborate on the forward pass, what kind of computations we'll do as we pick one training data. Okay, so our computations will be S1 equal to W1 times. Okay, let's pretend this is my index is J over here. So pretend X is like an array of data. Okay, in the MNIST data set, we have 60,000 images for training. Okay, and they provide 10,000 images for testing. Okay, so first we are focusing on just the training, so don't worry about the test so far. Okay, so let's pretend we went through our folder where all these images are already stored, and I'll show you how we'll read the images in a few minutes. And so our X array, let's pretend is 60,000 size array. So 0 through 59,000. So because over here we said for j equal to 0 to number of training data, so X of j, so first time I'll pick X of 0 as the training data, then X of 1, then X of 2, and so on, right? Okay, so now So in our forward pass, let's see if the matrix dimensions make sense. What was the W1? W1 was
784 by
784.
784 by 100.
Actually, 100.
Actually, no, it's 100 by 784.
The number of output by
Yeah, so did I write it wrong?
You raised wrong.
Okay, so this should be, output is 100. 784. Okay, so this is 100 by 784. Okay, what is x of j then? Okay, see, this will, the array that we will read it into will be 60,000, so it will be a two-dimensional array. So this is our training data basically. So 60,000 comma 784. So now this we will vary, it's like 0, 1, 2, 3. So anyway, so now this dimension will come out to be 784 by 1. Okay, what was B1? B1, I forgot to put the size for B1. If I have 100 neurons over here, 100 by 1, and B2 will be
10 times.
10 by 1, right? So, so anyway, so what will this produce as we do the multiplication? 100 by 1 plus B1 is 100 by 1. So will this be okay from a matrix?
Number of rows should be equal to number of columns, right? For a matrix.
Yeah.
100 by 784, 784 by 1.
Correct.
Yes.
Yeah, it will
That's
produce
fine.
100 by 1, right?
Mhm.
And then B1 is 100 by 1. We can add 100 by. So basically, this is a matrix multiplication. You guys agree? So this is a matrix multiplication. And this is a matrix addition.
Sorry to interrupt. It should be transpose, right? Because the rows has to be equal to column for the matrix multiplication.
No, see the way you multiply matrices is if you have an n by m matrix and you have an n by p matrix, these have to match as you multiply. So in our case, W1 is 100 by 784, right? And then x of j is 784 by 1. So these match, so the result will be 100 by 1. Okay, so in short, everybody agrees. This will be a regular matrix multiplication followed by matrix addition, okay? So if we are programming, let's say in C#, if we created a class matrix, and if we overloaded the multiply operator, overloaded the plus operator from your C++ background, even if you don't know C#, you'll remember we can overload the operators. So then our code will simply look like after the matrix class has been defined and the multiply operator plus operator has been defined on a matrix class, it will be simply one line of code. Okay. What about Python? Okay. So Python, what we'll do is we'll use a NumPy library. Okay, and let me sidetrack a little bit and give you some of the basic operations that we will do in NumPy from matrices point of view. Okay. So first of all, I know some of you are coming from an electrical engineering background and already know MATLAB. So NumPy tries to accomplish very similar to what MATLAB does. Okay. So there's in the very beginning, you will import the NumPy library. So provided you've already installed it in your environment, and I'll talk about the installation. So our typical code goes like this. Import NumPy as NP. Okay, then, suppose you wanted to create two matrices. So the question is, how do we create two matrices? So A equal to, so there's a couple of choices over here. There are a couple of classes available over here. One is like np dot zeros. Okay, and then in the Python, okay, there's a concept of a shape, especially for multi-dimensional arrays. So if we have, let's say, a 3 by 3 matrix, the shape of this will be 3 by 3 as an example. Okay, if you have a 100 by 1, shape will be 100 by 1. Okay, so this constructor for the, or this function for the zeros takes a shape parameter over here. Okay, so if to pick a very simple example, we wanted, let's say, 5 by 3 matrix. So you further have to put these parentheses over here because in Python that indicates a shape. Okay, so basically now it will create as 5 rows. So there will be 5 rows, 3 columns, and all will be initialized to zeros. Okay, now in our case, let's go to, for example, our W1 matrix, right? Because remember, all of these model parameters have to be initialized randomly. So there are a few choices over here. One possibility in Python is, before I go, so let me show you W1, how will we initialize this. So np.random .uniform. So there are different distributions available in Python. So uniform distribution basically means all values will span the range equally. The count of, so anyway, so then there are 2 parameters over here, low equal to, comma, high equal to, and size equal to. So in my opinion, that's one of the more useful functions for our purposes. Okay. So for example, if we wanted to initialize the weights from negative 0.1 to 0.1, okay, let's pick our example. In our example, what's the size? Size 100 by 784, right? So in Python, you will do like this. Further parentheses indicates the shape. So this will end up initializing the W1 matrix between negative 0.1 and 0.1, randomly uniform so that all particular values span the entire range. Okay, so very similarly, now let's go. Our X data has already been read from the file. How do we read it from the file? I'll go to the computer and show you in Python how you'll read the images. But because we are going to be using a sigmoid activation function in the beginning, and remember what does the sigmoid do? Squashes the output between 0 and 1, correct? So for the neural network to work nicely with the sigmoid, our inputs are coming as pixels, right? So they will vary between 0 through 255. So typically, if you're dealing with image type of data, what you will